Today we will discuss Lenz law and conservation of energy, right hand rule and induced EMF. Lenz law is used to find the direction of induced EMF or current. It is a convenient method for determining the direction of an induced EMF or current due to the electromagnetic induction, due to the phenomena of electromagnetic induction. The induced current will flow in such a direction so as to oppose the cause that produced it. According to Lenz's law, the induced EMF will flow in such a direction to oppose the cause that produced it. Obviously, the cause is change in magnetic flux. To demonstrate the Lenz's law, consider the n pole of the magnet towards the coil. Here, the n pole of the magnet is moving towards the coil. As the n pole of the magnet moves towards the coil, the magnetic flux linking the coil produces electromagnetic induction. So, due to the movement of this bar magnet, magnetic flux through this coil is changing. Due to change in magnetic flux linking in the coil, EMF is induced in the coil and phenomena of electromagnetic induction can be observed. According to Lenz's law, the direction of induced current will be such so as to oppose the cause that produces it. The direction of induced current or induced EMF is in such a direction that it opposes the cause that has produced it. So cause is the movement of this magnet towards the coil. So to oppose the movement of this magnet towards the coil is induce the current such that it will increase the magnetic field and it will behave like a north pole, because north pole of coil will oppose the north pole of the magnet to oppose the movement of the magnet. And in the formula of Faraday's law, we use negative sign, which shows that the direction of induced EMF is such that it opposes the cause which has induced it. It opposes the change in magnetic field. In the present case, the cause of the induced current is the increasing magnetic flux linking the coil. So the induced current will set up magnetic flux that opposes the increase in the flux through the coil. This is possible only if the left hand face of the coil become north pole, because when it will become north pole, so it will repel this magnet. Once we know the magnetic polarity of the coil face, the direction of induced current can be easily determined by applying right hand rule for the coil. So by knowing the polarity of the coil face, we can determine the direction of induced current. Similarly, if the north pole of the magnet is moving away from the coil, that is decreasing the magnetic flux through the coil, so the induced current through the coil will set up magnetic flux that attract the decrease in the flux through the coil. So the left face of the coil will become south pole and it will attract the north pole of the magnet. So by knowing the magnetic polarity of the coil, we can determine the direction of induced current, and in this case it is opposite to direction of this case, such that it is on right side, and we can determine it by the help of right hand rule. Lenz law and conservation of energy. Lenz law is a consequence of the law of conservation of energy. In the above example, When the north pole of the magnet is approaching the coil, the induced current will flow in the coil in such a direction that the left hand face of the coil becomes north pole, as we discussed in previous slide. The result is that the motion of magnet is opposed. The mechanical energy spent in overcoming the opposition is converted into electrical energy, which appears in the coil. Thus, Lenz's law is consistent with the law of conservation of energy. So in above case, as the mechanical energy spent in overcoming the opposition is converted into electrical energy in the coil, so we can say that Lenz's law is consistent with the law of conservation of energy. Fleming's right-hand rule and direction. By using Fleming's right-hand rule, we can determine the direction of induced current. To find the direction of induced EMF and hence current, Fleming's right-hand rule may also be used. According to Fleming's right-hand rule, stretch out the forefinger, middle finger and thumb of your right hand so that they are at right angle to one another. So we can stretch out three fingers of the right hand. We can stretch out the forefinger, middle finger and thumb of right hand such that they are at right angle to each other. If the forefinger points in the direction of magnetic field, thumb in the direction of motion of the conductor, then the middle finger will point in the direction of induced current. This middle finger is defining or pointing in the direction of induced current. Here we have another example. We have magnetic field and a current carrying conductor is placed in this magnetic field. So our right hand can be used to determine the direction of induced current. We can stretch out the forefinger, the middle finger and thumb such that they are at right angle to each other. The forefinger is pointing in the direction of magnetic field represented by red lines, and thumb is indicating the direction of force, and this middle finger is indicating or pointing the direction of induced current. So by using Fleming's right hand rule, we can determine the direction of induced current. Induced EMF. By Faraday's law, whenever a conductor is placed in a varying magnetic field, EMF is induced in the conductor, and this EMF is called induced EMF. We have discussed that in the phenomena of electromagnetic induction, we can move the conductor or either we can move the magnet. Relative motion of magnet and conductor is mandatory. It's up to us that we can move the conductor or we can move the magnet. So we have types of induced EMF. There are two types of induced EMF. First is dynamically induced EMF and second is statically induced EMF. Dynamically induced EMF. When a conductor is moved in a stationary magnetic field in such a way that the flux linking it changes in a magnitude, then the EMF is induced in this way. Is called dynamically induced EMF because magnetic field is stationary but conductor is moving. So due to the movement of conductor, the magnetic flux linking in the conductor is changing. So due to this type of induced EMF is known as dynamically induced EMF because in this type of induced EMF conductor is moving. So it is known as dynamically induced EMF. It is also called because EMF is induced in the conductor which is in motion. The conductor is in motion. That's why we call it dynamically induced EMF. Due to the motion of conductor in a magnetic field, EMF is induced in the conductor, and that is known as dynamically induced EMF. Statically induced EMF. When the conductor is stationary and the magnetic field is moving or changing, then the EMF induced in this way is called statically induced EMF. Now in this case, magnetic field is moving, conductor is stationary. Conductor is stationary, and due to the movement of magnetic field is changing through the conductor. Magnetic flux linked through the conductor is changing due to the movement of magnetic field. So the induced EMF in the conductor in this case is known as statically induced EMF, because the conductor is static, is stationary. It is so called because the EMF is induced in a conductor which is stationary. So in this case, conductor is stationary and magnetic field is moving. And EMF induced is known as statically induced EMF.